Module 2. Unit 3. Regression models. Regression models are a powerful tool in quantitative analysis used to examine the relationship between variables and to make predictions. The first step in regression analysis is identifying the variables and visualizing them in a scatter plot. A scatter plot allows analysts to see the relationship between two variables. For instance, if we plot the number of hours studied, x, against the exam scores, y, we can observe whether there is a trend that suggests a relationship between studying and performance. This visual representation is crucial for understanding the nature of the relationship before applying more complex statistical techniques. Once the scatter plot indicates a potential relationship, the next step is to develop a simple linear regression equation. This equation takes the form y equals a plus bx, where y is the dependent variable, x is the independent variable, a is the intercept, and b is the slope. The slope b represents the change in y for a 1-unit change in x, while the intercept a represents the value of y when x is 0. For example, if our regression equation is y equals 5 plus 2x, it means that for each additional hour studied, the exam score increases by 2 points, and if no hours are studied, the expected exam score is 5. Errors in regression analysis are referred to as residuals, which are the differences between the observed values and the values predicted by the regression model. Minimizing these residuals is essential for creating an accurate model. The percentage of the variation in the dependent variable that is explained by the regression equation is measured by the coefficient of determination, denoted as R2. An R2 value of 1 indicates a perfect fit, meaning all the data points lie exactly on the regression line, while an R2 value of 0 indicates that the model does not explain any of the variation in the dependent variable. In cases where every sample point lies on the regression line, meaning all errors are 0, the correlation coefficient would be -1 or 1. A correlation coefficient of 1 indicates a perfect positive relationship, where increases in the independent variable lead to proportional increases in the dependent variable. Conversely, a correlation coefficient of -1 indicates a perfect negative relationship, where increases in the independent variable lead to proportional decreases in the dependent variable. Managers at the company Smith & Brown suspected that several sales representatives were claiming unusually high expenses for client meetings. To investigate, they took a sample of 150 expense reports and developed a multiple regression equation relating expected meeting cost, y, to the number of hours spent in meetings, x1, and the number of clients met, x2. The resulting equation was y equals 75 plus 30 x1 plus 15 x2. Using this model, if Jane Doe reports a meeting where she spent 4 hours with 8 clients, the expected amount she should claim as expenses is calculated as follows. Y equals 75 plus 30 times 4 plus 15 times 8, which equals $315. Another example involves developing a regression model to fit given data points. Consider the dataset. X equals 1, 1, 2, 2, 9. Y equals 1, 1, 2, 9. The regression model to fit this data, rounded to 2 decimals, is y equals 0.07 plus 0.98x. This equation suggests that for each unit increase in x, y increases by approximately 0.98 units, starting from an intercept of 0.07. Understanding the assumptions used in regression is crucial for interpreting the results accurately. These assumptions include linearity, independence, homoscedasticity, and normality. Linearity assumes that there is a straight-line relationship between the independent and dependent variables. Independence assumes that the residuals are independent of each other. Homoscedasticity assumes that the residuals have constant variance at every level of the independent variable. Normality assumes that the residuals are normally distributed. Residual plots can help identify problems with these assumptions by showing patterns that indicate deviations from the expected conditions. The F-test in a linear regression model is used to determine whether the overall regression model is a good fit for the data. It compares the model with no predictors, the mean of the dependent variable, to the model with the predictors included. A significant f-test indicates that the model explains a significant portion of the variance in the dependent variable. In addition to simple linear regression, students will learn how to develop multiple regression models which involve more than one independent variable. These models are used to examine the effect of multiple factors on a dependent variable. For example, a multiple regression model could be used to predict house prices based on factors such as square footage, number of bedrooms, and location. The equation might look like this: price equals A plus B1 square footage plus B2 number of bedrooms plus B3 location. Dummy variables are used in regression models to represent categorical data. For example, if we have a categorical variable like type of house with 3 categories, detached, semi-detached, and apartment, we can create 2 dummy variables to include this information in the regression model. Dummy variables take values of 0 or 1 to indicate the presence or absence of a category, allowing categorical data to be incorporated into regression analysis. Determining which variables should be included in a multiple regression model is an essential step in model building. Variables should be selected based on their theoretical relevance and statistical significance. Including too many variables can lead to overfitting, where the model describes the random noise in the data rather than the underlying relationship. Conversely, omitting important variables can lead to underfitting, where the model fails to capture the essential patterns in the data. Transforming a nonlinear function into a linear one for use in regression involves mathematical techniques such as logarithmic transformations. For instance, if the relationship between x and y is exponential, y equals a times b to the power of x, taking the logarithm of both sides transforms into a linear relationship. Log y equals log a plus x times log b. This allows linear regression techniques to be applied to the transformed data. Recognizing common mistakes in regression analysis is important for avoiding errors and ensuring accurate results. Common mistakes include ignoring the assumptions of regression, misinterpreting the coefficients, overfitting the model, and failing to validate the model with new data. By being aware of these pitfalls, analysts can improve the reliability and validity of their regression models. Unit 4. Inventory Control Models. Inventory control models are essential tools in managing the supply chain and ensuring that the right amount of inventory is maintained to meet demand without incurring unnecessary costs. Inventory control involves several key components. These include planning what inventory to stock and how to acquire it, forecasting the demand for parts and products, and controlling inventory levels. Effective inventory control ensures that businesses can meet customer demand while minimizing the costs associated with holding and ordering inventory. One valid use of inventory is the decoupling function, which allows different parts of the production process to operate independently. Inventory also helps avoid shortages and stockouts, ensuring that products are available when needed. Additionally, inventory can smooth out irregular supply and demand, helping to maintain steady production and sales levels. The economic order quantity, EOQ, is a fundamental concept in inventory management. EOQ is the optimal order size that minimizes the total cost of inventory, which includes both holding costs and ordering costs. The EOQ formula is derived from the trade-off between these two types of costs. If the EOQ assumptions are met and a company orders more than the EOQ, the total annual holding cost will be greater than the total annual ordering cost. This imbalance leads to higher overall inventory costs. To calculate EOQ, the formula used is EOQ equals the square root of 2ds over h, where d is the annual demand, s is the ordering cost per order, and h is the holding cost per unit per year. For example, consider Lisa Green's electronics store, which uses 4,000 microchips per year, purchased at $20 each, with a holding cost of $2 per microchip per year, and an ordering cost of $25 per order. Using the EOQ formula, EOQ equals square root of 2 times 4,000 times 25 over 2. 2 times 4,000 times 25 is 200,000. Divided by 2 is 100,000. 100,000 squared is 316.23. Thus, the EOQ for Lisa Green's electronics store is approximately 316 units. The reorder point, ROP, is another critical measure in inventory control, representing the inventory level at which a new order should be placed to avoid stockouts. The ROP is calculated based on the lead time demand, which is the product of the lead time and the average demand during that lead time. For instance, if the lead time for receiving new inventory is 2 days and the daily usage rate is 10 units, the ROP would be ROP equals lead time times daily demand equals 2 times 10 equals 20. This calculation ensures that a new order is placed when there are 20 units left in stock, preventing stockouts during the lead time. In the production run model, the maximum inventory level will be less than the production quantity because inventory is used up as it is being produced. This model considers both the production rate and the demand rate. The formula for the maximum inventory level in a production run model is maximum inventory equals P minus D over P times Q, where P is the production rate, D is the demand rate, and Q is the production quantity. The inventory position is defined as the total of the on-hand inventory plus the on-order inventory. This measure helps businesses keep track of their overall inventory status and make informed decisions about when to place new orders. A just-in-time JIT system is a lean inventory management strategy that aims to minimize inventory holding costs by receiving goods only as they are needed in the production process. A JIT system usually results in a low annual holding cost because it reduces the amount of inventory held at any given time. This system relies on precise demand forecasting and efficient supply chain management to ensure that materials are available when needed without holding excess stock. Manufacturers use material requirements planning, MRP, when the demand for one product is dependent on the demand for other products. MRP is a system for planning and controlling inventory that takes into account the dependent demand of components in the production process. It ensures that the necessary materials are available for production at the right time while minimizing inventory levels. Safety stock is additional inventory held to protect against variability in demand or supply. It acts as a buffer to ensure that there is enough inventory to meet unexpected increases in demand or delays in supply. The amount of safety stock required depends on factors such as the variability in demand and lead time, the desired service level, and the lead time demand. Marginal analysis is used to compute single-period inventory quantities by comparing the marginal benefits and marginal costs of different inventory levels. This analysis helps businesses determine the optimal order quantity for a single period, balancing the costs of ordering too much or too little inventory. Inventory control models also include handling inventory problems that allow for non-instantaneous receipt and quantity discounts. In cases where inventory is received gradually rather than all at once, the EOQ formula must be adjusted to account for the production rate. Similarly, quantity discounts, which provide price reductions for larger order sizes, require an analysis of the trade-offs between the reduced purchase cost and the increased holding cost. Effective inventory management requires careful planning and analysis. Businesses must forecast demand accurately, plan their inventory levels, and control their stock to minimize costs and meet customer needs. Various inventory control models and techniques help businesses achieve these goals by providing structured approaches to managing inventory.